In a previous lesson, we talked extensively about the volcanism that has shaped the Yellowstone region over the last 50 million years, with a lot of focus on the major eruptions of the Yellowstone supervolcano, 2.1 million years ago, 1.3 million years ago, and 640,000 years ago, and how the Yellowstone hotspot today continues to supply the energy to fuel the hydrothermal features, which are a hallmark of the Yellowstone region. In this lesson, we're going to talk about some other aspects of the geology of Yellowstone and Grand Teton National Parks. And we're going to focus on the effects of glaciation in the past, and some of the effects and the signs of faulting in the region of Yellowstone and Grand Teton. And then there'll be some little extras at the end here. So this will be our final lesson before our trip. All right, so let's get started. Mountain building events are called orogenies. And when we look at a specific chain of mountains, we can study the geological processes that gave rise to those mountains. And when it comes to the Yellowstone and Grand Teton region, two geological processes which have contributed to the creation of the mountains in the region are one's called the Basin and Range Province stretching. And so here's a picture of, and so Yellowstone is up here, and the Basin and Range region of the North American plate. What's happening here is the North American plate is stretching and thinning, and this gives rise to faulting, which looks like this. These are called normal faults or extensional faulting, where you have regions of the crust, regions of the North American plate that are pulling apart. And this is what's happening in the Teton Range. What you have is at a normal fault line is, as the fault pulls apart, one side of the fault is driven upward and the other side of the fault falls downward, creating so on the side that you have uplift, you get a mountain chain, and where you have the fault block falling, over time it fills in with alluvium and other deposits, but you basically get a valley, a flat valley. So this type of process defines lots of the mountain chains in the Rocky Mountains, and it's what's called basin and range, because you have these basins, these ranges, mountain ranges, separated by these basins. That's created by the stretching of the North American plate. Another process that's driving mountain building, that has contributed to mountain building in the area of Yellowstone and Grand Teton, it's called the Idaho-Wyoming thrust belt. So what you have here is you have regions of you have faults where one region of crust is being thrust against another piece of the crust. And when this happens, oftentimes what happens is at a thrust fault is you have older rock that's pushed on top of newer rock. So that's a hallmark of this type of faulting. So in this slide right here, we have a close-up of the eastern slope of the Teton Range. And so the Teton Range is very new by mountain standards. Evidence suggests that most of the uplift has occurred in the last few million years. And the amount of uplift coupled with the amount, so the fault block on the western side of the fault has been rising, and the fault block on the eastern side has been falling. And the difference between this rising and falling is like 20 or 30,000 feet over the course of 2 to 5 million years. And the mountains aren't that high. So why? Well, as they've been rising, they've been eroding due to the weather and also glaciation, and the valley, as it falls, has been filling in with glacial deposits and alluvium material that's been transported by water, so sediments filling it in. But the movement along this fault line, and sometimes periodically, infrequently, but periodically, can be pretty abrupt. And if you've had recent movement along the fault line and there hasn't enough time hasn't passed for evidence of that movement to erode away and be obliterated, what you get is a scarp. And so here's a scarp. You have to be on the lookout for this scarp when we're actually at the Tetons. It's actually evidence that this side of the fault block moved up and or this side of the fault block moved down, and you get this separation along the fault. And it's visible. All right, so we'll be on the lookout for that. So speaking of earthquakes in this region, they do happen. You have active faults. You have active geology, and you have faults that are periodically going to move. And in 1959, there was a magnitude 7.2 earthquake to the west, northwest of the center of Yellowstone National Park, along in the vicinity of a lake on the Madison River called Hebgen Lake. And this earthquake created a landslide, and this landslide, coupled with the amount of water it displaced, killed 28 people who were camping along the Madison River on this night when the earthquake occurred. And the landslide also created a blockage of the Madison River, which created a new lake, which appropriately is called Earthquake Lake. Let's talk about glaciation and how it's affected the landscape of Grand Teton and Yellowstone National Parks. Essentially, for the last 2.5 million years, during the entire period of geologic time called the Quaternary period, there's been a repeated advance and recession of an ice sheet that's covered a large portion of North America, called the Laurentide ice sheet. And during periods of this time, there's also been an ice sheet that's been covering a more localized ice sheet that's been covering the area of the Yellowstone Plateau. And so in Yellowstone and Grand Teton today, what you see is evidence of the two most recent periods of glaciation associated with this local ice sheet in the northern Rocky Mountains in the Yellowstone Plateau area. The one period of glaciation is called the Bull Lake Glaciation, which lasted from about 200,000 years ago to about 130,000 years ago. And so in this picture here, you can see in red the extent of glaciation of the glacier during the maximum extent during the Bull Lake Glaciation period. And then you also see evidence of glaciation in the glacier called the Pinedale Glaciation, which had its maximum extent about 20,000 years ago and lasted to about 10,000 years ago, which coincides with the end of the Pleistocene epoch, when the first Paleo-Indians were starting to inhabit this region. So what actually happens when you have glaciation? You have snow that accumulates faster than it can melt, and the snow becomes consolidated into an ice sheet, and the ice sheet is so massive and so heavy that it flows. It flows downhill, and as it flows downhill, it picks up debris, picks up rock. It scours the landscape, and when it melts, it can leave behind the rock and material that it's been carrying with it. And so in this picture here, you see that essentially the ice sheet, the glacier, moves along the current trajectories of the major rivers flowing out of the Yellowstone Plateau. The Madison River, the Yellowstone River, And the, the glaciers actually help to shape the landscape and define the river valleys that exist today. So one of the features, one of the things that you'll see in a landscape, which is evidence of past glaciation, is a moraine. And so what this is, so at the time when Yellowstone and Grand Teton national parks were covered in these ice sheets were thousands of feet thick. And as this ice flows and scours the landscape, it's picking up debris, it's picking up rocks, and these rocks get carried along with the ice as it flows downhill. And so as this material flows, it's going to be deposited somewhere uh, downstream, if you will, in the direction of flow of the glacier. And where you have these deposits, you have moraines. So in the Grand Tetons, what you'll see is that in some places in the landscape, you'll have these hills which are covered in vegetation. And what these actually are moraines of these past massive glaciers. This material that's been deposited here is just more conducive to the growth of forests than the material that makes up most of the valley floor. So you get these areas of vegetation, trees, these forests on top of these moraines. And so we'll actually we'll drive to the top of one of these moraines and take a look at the valley from on top of it when we're there. Um, and here's a much smaller moraine, much more recent moraine from a glacier somewhere. I don't even know if that's in the Tetons. Um, but you have this deposit of loosely packed debris here that's being carried along by the ice as it flows. So the moraine when you have a period of glaciation, there's going to be some location of maximum extent for the glacier, and it's that place where the ice is melting faster than it flows, and that's as far as the glacier progresses. And so where this happens, you can have the sort of longer term deposition of material as the glacier melts, giving rise at the maximum extent of the glacier's movement. So giving rise to a moraine, and it's called a terminal moraine because that's the furthest extent that the glacier achieved, a terminal moraine. Another feature that you'll see in a landscape, which is evidence of past glaciation, is are boulders just strewn across the landscape in places where you wouldn't expect there to be a boulder. They're called glacial erratics. These boulders were just carried along for a ride in the glacier as the ice flowed, and then when the glacier melts, these boulders are left behind. And so when we're in Yellowstone, be on the lookout for glacial erratics. And one thing you might notice is that um, trees may become established. You might be looking at this, grassland, wide open space, and then there's a glacial erratic, and then there's a tree that just has established itself right next to a glacial erratic and has grown there. And the reason it can grow there is because this boulder provides a little extra shelter for the tree and shade for the soil in the vicinity of the boulder so it can retain more moisture. It's a place that's more conducive to the growth of trees. So we'll be on the lookout for that when we're at Yellowstone. Some other features that you'll see in a landscape affected by glaciation are glacial horns. And glacial horns are mountain peaks which have been formed by the scouring effects of glaciers moving around and taking a mountain and filing it down to a sharp point. Um, Another feature you'll find, they're called arates, and I spelled that wrong. Arate with a little accent there. And Arates are these are areas where you had two glaciers that are scouring opposite sides of a mountain and creating a narrow region, a narrow structure of rock that's kind of connecting the two mountain peaks. And okay, so we'll be on the lookout for that and see if we see any evidence of arates or glacial horns in the Tetons. Another feature of the landscape, which will show us that there's been past glaciation, are called kettle lakes. And we'll see some kettle lakes, let's see, in Yellowstone, kettle lakes in the Lamar Valley. We'll see some kettle lakes. So what happens? These are just small little lakes. And what happened is you had a big chunk of ice that was carrying along a bunch of rock and debris, and when the glacier melted, you had this chunk of ice that kind of in an area where it was kind of scoured out a little bit, and the ice was carrying some material. And when the ice melted, that material settles in to this depression, and that material makes the soil less permeable to moisture, to water. So you get a lake. You get this little lake that forms. They're called kettle lakes. So as mentioned earlier, as you have movement along the Teton Fault here, the fault block to the west is rising, and the fault block to the east is falling. But this area where you have the fault block falling is constantly filling in with sediment, fine sand and silt and gravel, material that's collectively transported by the flowing streams and rivers and floods. It's called alluvium. And alluvium can tend to create very fertile soil. And eventually, after many thousands of years, that alluvium can form sedimentary rock, like sandstone and the like. So I have a few more slides that don't deal with glaciation or faulting and mountain building, but they're interesting things that we'll see while we're out there exploring the landscape of Yellowstone and Grand Teton National Park. One of the things we'll see is we'll see this lake. It's called Indian Lake. It's on the northern shore along the northern shore of Yellowstone Lake. And this lake is a crater. It was created by a hydrothermal explosion or a phreatic explosion, phreatic eruption, a hydrothermal eruption, relatively recently, about 3,000 years ago. So what we had here is an underground reservoir of superheated hot water, and something happened to release a little bit of that pressure. And when that happened, when you had that pressure release, that initial pressure release, you had large quantities of water flash to steam very quickly, creating an explosion. And pieces of this explosion have been found 3 kilometers away from the pond. And although it's not shown here, there's a much bigger crater of a hydrothermal or phreatic eruption really close to this Indian pond. It's called Mary Bay. It's actually a lobe on Yellowstone Lake. All right, so here's another really interesting thing we'll see. So what we're looking at here is a close-up of one of the peaks in the Teton Range, Mount Moran. And near the peak of this mountain, you have this really interesting feature where you got some black rock and some light colored rock surrounded by this more marbly looking rock. What the heck is going on here? So what we have here is while this piece of Mount Moran was still underground millions of years ago, what you had is you had basalt that intruded into a gap in 2.8 billion year old metamorphic granite called gneiss. And this basalt hardened, that's what you're seeing right here, this black region, this basalt hardened, uh, uh, creating an igneous rock called diabase. It's basalt with slightly larger crystals in it because it cooled more slowly than basalt that hardens when it comes to the surface. And then at some point in the past, there was some alluvium deposited on top of this when it was still the valley floor, creating a cap of sandstone. So you have 2.8 billion year metamorphic granite, gneiss, all around. And you have this intrusion. It's called an intrusive dike. That's what this is called, intrusive dike, or a magmatic dike of diabase. That's 780 million years old. And then you have this sandstone cap, which is only 530 million years old, of sedimentary rock. So in this one picture, you have metamorphic rock, igneous rock, and sedimentary rock all in the same place, all of different ages. It's a really cool feature of this mountain.